All right, let's first go over what we're supposed to be solid on from before break, and then we'll talk about the new section we're starting. So we are going to be asked to solve quadratics, and by the end of this semester, we should be 100% solid on all three methods. So solving this first one, we are always going to attack these with the same evil plan. Our goal number one is, can we solve by factoring? It is by far the fastest and easiest method, the most proficient for most students. So we're always going to try to check first. Is there a way for me to factor what times what equals negative 24 and subtracts to give me negative 2? So if you guys are thinking 6 and 4. By the way, if you're not thinking 6 and 4, we go off to the side. What are all my possible factors for 24? Make that list. Look to see these all multiply to give you the negative 24, but which ones subtract to give you the 2? So it's got to be these as your factors. So the 6 is going to have the negative. 4 minus 6 would be negative 2. So x minus 6 is my first factor, and x plus 4 is the second factor. But they don't just want us to factor, they want us to solve. So we keep going by setting each factor equal to 0. By zero product property, we solve and get the solutions. So what did I just find? I found that I have two real solutions to this quadratic. If I were to graph it, it touches at negative 4 and at 6. These are my two solutions, my roots, my zeros. They are the opposite signs from the factors. If the factor was a negative 6, the solution is a positive 6. We just learned that we can actually write these as x-intercepts. If we take these answers and write them with a comma 0 in intercept form. So these are my x-intercepts as well. So evil plan number one, solved by factoring, worked for this problem. This was factorable. I am able to get the solutions. It doesn't mean I can't use the other methods. I could have solved this by completing the square, and I could have solved this by the formula, but I'm trying to find the most efficient formula now. What's the best way for me to solve it? Okay, let's try number 2. Okay, for this one, we're looking to see if it's factorable. Evil plan, always start with the same idea. Can we solve by factoring? And when I go do what times what equals 10 and subtracts to give me negative 6, I'm thinking, okay, wait, 1 times 10, no. 2 times 5, no. Shoot, it's not factorable. Factoring does not work in all cases. So evil plan number 2, let's solve by completing the square. Okay, let's go see if this one's set up nicely for that. In order to solve by completing the square, I want to look at my b. If b is even, then it's preferable to solve by completing the square. When b is odd, no, I'm not going to want to do that. We'll see in the next one. So in this case, we go move the constant, b work, I'm going to be adding 9 to both sides. Now, where does this x minus 3 factor come from? These are the two factors that would give me this perfect square. I can get the negative 3 from this b work, or I can just look up at the b again and go half of b would be negative 3. Now I'm ready to square root both sides. And I'm like, wait a second, square root of negative 1. By definition, we were taught right before the break that the square root of negative 1 is I. It's an imaginary number because there's no real root that could give me a result of negative 1 under that radical sign. So we have the imaginary I to stand for this by definition. So giving this final answer, when I add 3 to both sides, it's going to be 3 plus or minus I as my final answer. What did I just find? I found that I have 2 non-real roots, or no real roots, or 2 imaginary roots. So what the heck is an imaginary root? If I went to go graph this, it's 2 places where this equation is equal to 0. These 2 spots are my roots, but notice that they do not touch the x-axis. If they do not touch the x-axis, there are no x-intercepts, no solutions, no real roots, no zeros. It is 2 imaginary roots because they're floating here up above. Okay, let's go look at number 3. Again, we're being asked to solve this quadratic, and this time it's x squared minus 3x plus 18. So here I go with my evil plans again. Evil plan number 1, solve by factoring. Okay, this is looking promising. What times what is 18? I'm thinking 6 and 3, but then it's got to give me a negative 3, so I'm like, wait, 6 minus 3 or 3 minus 6. I'm going to need a negative on here to make this true, but negative times positive 3 does not equal positive 18. Oh my gosh, this is actually not factorable. If this was a negative 18, it would be factorable, but so evil plan number 1 doesn't work. Evil plan number 2, completing the square. When I go to do this one, and I'm thinking about the b work, I'm thinking negative 3 divided by 2 squared is 9/4. Ew. I don't want to complete the square with a fraction. Now, could I do this with common denominators and blah, blah, blah? Sure, but it's not my preferable method. Whenever you have an odd b value, I'm not going to prefer to use complete the square. I don't want to do it. Okay, so what's that leave me in my evil plans if I can't do that one either? What's my tried and tested, always can be used? The quadratic formula. The quadratic formula can be used no matter what, on any quadratic. Get me ABC, plug into this formula. A is 1, B is negative 3, C is 18. Whenever I get ready to plug in, I get the parentheses ready. All right, so negative b turns into negative 3. Negative 3 squared is b squared minus 4 times a times c all over 2a. Notice where these plugged in and see how you did on that. Did you get b as negative right here? Did you get a as that positive 1? And did you get C as 18? All right, so the front would become positive 3. The bottom becomes positive 2. I always simplify the front and the bottom first. And then underneath, negative times negative is always going to give you a positive for this b squared. Be careful with your sign. And then 4 times 18 is minus 72. So 3 plus or minus root negative 63. So if you're able to get this far on the quadratic, it means you do understand the formula. If you can get further, you understand the simplifying. So let's go off to the side and talk about root negative 63. This would be positive root 63 and then negative 1. 63 breaks up into root 9 and root 7. Why am I interested in root 9? Because 9 is a perfect square. Root 9 gives me 3. Negative 1, the square root of negative 1 by definition is I. and then root 7 stays root 7. Notice what root negative 63 simplifies to. This becomes this. So here I go. X equals 3 plus or minus 3i root 7 over 2. What did I just find? I just found my two non-real roots, or my two imaginary roots. All right, so we need to be solid on solving by all three methods by the end of this semester. Which one are you feeling is your strength? Which one are you feeling like you need to review before our upcoming test? All right, let's start to talk about the next section, 5.6, which is solving non-linear systems. So before we can move on to talking about that new Math 2 topic, let's talk about a Math 1 topic that's similar. Okay, in Math 1, we solved linear systems. We solved it by elimination, substitution, and graphing. Those were our three methods of solving linear systems. When we solved a linear system, sometimes we got two lines that touched once. This was known as one solution to the system, and that was called our point of intersection, right? We got one dot where they both touched. Sometimes we had two lines that never touched. This was known as no solution, and this is when they were parallel lines. All right, what about when you got a line and then we had another equation where pretty much they were the same line, not pretty much, but they were the same line, so they touched everywhere. They were the same line. This was called infinite solutions. So we're basing this new concept on this old concept, on the fact that last year we had two lines and we found where they touched, or never touched, or that they touched everywhere. Now in Math 2, nonlinear systems, we're going to see that it's not always two lines. And so since we're studying parabolas, we're going to have a situation where you have one parabola and one line, and they touch once. If you have a parabola and a line that touches once, that is called one solution again. So just like last year, I'm going to be giving you a graph and I'm going to say, hey, what's the solution to this nonlinear system? And you're going to go, oh, it's right there, that point of intersection. What if I give you a parabola and a line that never touch? This is called no solution again, because they never touch. So just like Math 1 last year, two lines that never touch, there can be a parabola and a line that also never touch. That was called no solution. So one solution, still touching once. No solution, never touching, still. Now, it is possible to get two parabolas that land right on top of each other. That would be called infinite solutions, but we're not going to see that case. What we are going to see a lot of this chapter is something that we didn't have with lines last year. This is the new idea. And that is, because it's a curved parabola, this time it's going to be able to touch twice. This is called two solutions. So what are we going to see on this? We're going to see that there might be 0, 1, or 2 solution possibilities. So we just started with this general concept. Half of your quiz on Apex is just going to be asking you to say, what is the solution with a picture? But what are we going to focus on Wednesday? Just like you used methods of algebra to solve linear systems, Wednesday's class is going to be how to use algebra to solve nonlinear systems. And factoring is going to come into this as well. Besides that, we're also going to use graphing to solve nonlinear systems. So our notes on Wednesday are going to focus on practicing using the algebra to solve and practicing using the graphing to solve. Before Wednesday's class, I really need you to do the study guide. So it's not your first time seeing these methods when you do them with me on Wednesday. We are going to be taking the Apex quiz 5.6.3 in Wednesday's class.